Okay, so first of all, we can see that sigma 1, 2 is an odd function of k, which also makes sense, right? The amount of force it takes you to shear a material by this amount plus k should be the opposite of the amount of force it takes you to shear it by minus k. All right, if I write it here again, sigma 1, 2 is, I'm going to write it like this, mu k, where mu is this quantity. Is a function of k squared. I remember that w is function k squared, so it's derivative of function k squared. So mu is an even function of k, and so mu times k is going to be an odd function of k. And so it means that doing the curve fitting, I've seen that in the literature. For instance, people have something like that, sigma 1, 2, k, and they say, oh, well, it's not linear, so we're going to say sigma 1, 2 is something like a k to the power b. And I'm going to adjust my b to get to the nice power law. But unless b is an odd integer, and that's not the case in the fitting, right? Or people come up with number like 1.3 or whatever, then you cannot write this because it's not an odd function of k. Not correct for p when b is not an integer. Right, let's compute mu. Mu, that's called the shear modulus of non-linear elasticity. Let's see what happens for neo-Hookean, for instance. Neo-Hookean, that's when W is of this form. That tells me that mu is going to be 2 times the derivative W with respect to I1, that is with respect to I1 is mu 0 over 2 times 2, that's just going to be mu 0. And then derivative with respect to I2 is 0, there's no I2 dependence here. Monet-Rivlin, that's when W is C1 over 2 plus C2 over 2, where C1 and C2 are positive constants. If I do the derivatives here, I'm going to find that mu is C1 plus C2. So for those two materials, I have a constant mu, constant shear modulus. And so those two models will be appropriate if in my data I find a straight line between sigma 1, 2, and k. If I don't, then I'll have to think of another model. For instance, the jet model, if you remember, it was like this. So if I differentiate this with respect to I1, the minus is going to come out, the 2 is going to come out, the gn is going to come out. I'm going to end up with mu 0, 1 over, just differentiate the log. I1, I go back up, is 3 plus k squared. So I1 minus 3 is just k squared. Mu 0 times jm minus, oops, k squared. So in this case, it's not a constant. And finally, for the full material, you can differentiate, or I'm just giving you the result now. It's boring to have somebody do differentiations, but you will find mu 0 exponential bk squared. Right, so for those first two examples, it would be appropriate if you add data like this. For those last two, it would be appropriate if you add data like that, where it starts increasing. Yeah, other increases in a exponential manner, you want to take the form. If the increases and seems to go towards an asymptote, you want to use the jet material, and so on and so forth. So just to show you, I've lost that slide now. Just to show you an example, here I've done experiments a couple of years back on brain using a pig brain, and that's the type of curve we got. This is the data, those stars are the data, and you can see that they will be really approximated by a straight line. And that's a measure of the goodness of the fit, 99. And that's all the way to k equals 1. K equals 1, that means it's tilted at 45 degrees. That's pretty large deformation. And so you can conclude that the brain behaves as a Mooney-Rayleigh material, or Nehru-Hooken, or any material that will give you a linear, any model that will give you a linear behavior in simple shear. And there's no need to go to foam or jet material. Interesting. I think so. Okay. What else can we say? Oh yeah, we can find a nice connection, and I'm going to call it universal because it works for any W, universal relation. And that's the one that was in the assignment. Here, if you do sigma 11 minus sigma 22, right? If I do sigma 11 minus sigma 22, the p's are going to cancel out. The W1s are going to cancel out. I'm going to be left with 2k squared W1. And then the W2s are going to cancel. I'm going to be left with plus 2k squared W2. I'm going to find sigma 11 minus sigma 22 equals 2k squared W1 plus 2k squared W2 k squared, but 2W1 plus W2, that's mu times k, and mu times k, that's sigma 11, or sigma 12. So in the assignment, you asked to prove this relationship using another equation, which was the fact that B and T commute for isotropic material. But you can also write it directly from doing this subtraction, sigma 1 minus sigma 2 2. And that's the relationship between the normal stresses, sigma 1 sigma 2 2, and the shear stress, sigma 1 2. Very nice. In particular, you can see that sigma 1 1 is always distinct from sigma 2 2 in simple shear. Like sigma 1 minus sigma 2 2 cannot be 0 in simple shear. And that's called the Poynting effect. Okay. I'm just going to go back here and write the components of the force that need to be applied on this plate here. Apply traction. So the normal to this face is E2. So the traction is going to be, I'm going to write it in the current configuration, is going to be sigma TE2, right? It's going to have components, 3 components, sigma 2 2, no, sigma 1 2, sigma 2 2, and sigma 3 2, or sigma 2 3. So it's going to have a component along the E1 vector, sigma 1 2, and that's the shear force you're going to apply. And then it can also have a normal component and another shear component, 3 2. Although we saw that sigma 3 2 is 0, so I didn't need to represent it here. Sigma 2 2, it might be 0. So what does that mean? It means that to create the simple shear, I not only have to apply a shear force to pull like this, but I also have to apply a normal force if sigma 2 2 is not 0. Either I have to push or pull. That I have to guide the plate to stay in a horizontal plane. If I don't, it's going to lift up or come down. Let's see this in more details now. If I do, oh yeah, what I'm going to do is I'm going to assume that this face here is free of traction. Oh, sorry. Sigma E3 equals 0. Right, I'm just shearing by applying forces on the plate on top there, and then nothing on this side. So if sigma 3 3 is sigma times E3 is 0, it means sigma 1 3, sigma 2 3 are 0. That's acquired already, but it also means that sigma 3 3 must be 0. So I'm going to write it now. Sigma T3 equals 0. And and that's good. And also, so that means that minus P plus 2W1 to W2 must be 0. And so that's going to help me find P. And so I'm going to get rid finally of this indeterminate quantity, right? P is going to be 2W1 plus 2W2. Remember, we introduced it because of incompressibility, but I did say we will have to eliminate it or determine it one way or another. Here we have done that through the boundary condition, saying that there's no stress on that phase. So if P is this, then I can substitute into the expression for sigma 1,1 and sigma 2,2. That's going to eliminate the W1 and the W2. I'm going to be left with sigma 1 is 2k squared W1, and sigma 2,2 is, that's going to be minus, and minus plus, so it's going to be 2k squared W2. Sigma 1,1 is 2W1k squared. 2 is 2. Oh, there's a minus. W2k squared. And that shows you that there has to be normal forces. There has to be either sigma 1,1 or either sigma 2,2 or either both of them. They cannot be 0 together. Right? If both sigma 1,1 and sigma 2,2 are 0, then it would mean that W1 and W2 are 0. Then W will not depend on I1 and nor I2, and then there will be no W. Sigma 1,1 and sigma 2,2 cannot be 0 simultaneously. So we need to apply normal forces. So let's look at those examples I had earlier. Newtonian, mu 0 over 2 I1 minus 3. Newtonian, or in fact, for that matter, Gent and Fung, you can see these are 3 examples of strain energy that do not depend on I2. So if they do not depend on I2, W equals W of I1 only, then W2 is going to be 0. Remember, W2 means dW dI2 is going to be 0, and then sigma 2,2 is going to be 0. So that means I don't need to supply a vertical force to create my simple shear, right? I don't need that component here to create the simple shear. On the other hand, if I look at Mooney-Rivlin, I will find that sigma 2,2 is going to be minus sigma 2 times minus C2k squared. Here for the Mooney-Rivlin, I need to supply a force. So that's really interesting. What if I don't supply a force? Then the plate should go up and down. Or what if I have the plate and I drill the hole in the plate? At that hole, there's no contact between the sample and the plate, and so the sample should bulge through the hole or cave inside. It should not remain flat if it is Muni-Rivlin, or it should remain flat if it is Neo-Hookean Fung or Gent. And I just show you now is the experiment I did with the brain. As you can see, the bottom plate and the top plate are now, they're not above one another. The sample, so this is seen from above. The sample is between those two plates and it has been sheared. And there we drill the hole in the top plate. And it's hard to see, but it's hard to capture on the picture. But with the naked eye, you could see that the brain was bulging through the hole. That means that we have to provide a force, a normal force, to keep it flat, to create the simple shear, perfect simple shear. Here I show you finite element simulations, and we could see that there is a bulge. Of course, the same emulation here we took the Muni-Rivlin material, but you can see in the finite elements, you can see here, so it's a more realistic deformation. It's almost homogeneous everywhere, right? It's the same color almost everywhere, except here maybe it's a bit colored because of that singularity we created there. And also the parts where there's strong inhomogeneity. You can see that the faces are not straight anymore. So that's another phenomenon. I'll talk about that now. But from observation, you could just deduce for brain, you could see that you need, oh, not deleting for some reason. Okay. Didn't like having to go to. No. Whoa. What is going on? Okay. Stop that. That didn't look good. Again. Like my TV was imploding. Ah, lost my iPad. Okay, I do. Nah, some problem. Okay, I'll stop the recording for a